So we're going to start this video by making another connection with our linear components, or linear version of things. So when we find the net force acting on something, it's going to add up to be equal to m times a. And then we got our net force equation after. So ma would be equal to, and then we'd add all the forces together. And that's the relationship between mass and acceleration force. Okay, there's a similar relationship here for rotation. So if we think about the rotational version of mass, which is rotational inertia or moment of inertia, and the rotational version of acceleration, angular acceleration, then this will be equal to the rotational version of force, which is torque. So if you add up all the torques acting on something, it'll be equal to the moment of inertia times the angular acceleration. And we can do just like we did net force equations, we can do net torque equations. We'll add up all the torques acting on an object, and the sum of those torques should be equivalent to the moment of inertia times the angular acceleration. So let's give it a try. So here we have a scenario where there's an elephant and a mouse standing on a platform, and so what we can say here is that the net torque on this system is going to be equal to the sum of the two torques, and then for this we want it to be in equilibrium. So we'll talk about what that means in a second. So the first step here would be to we're basically going to see how these two guys balance each other out, and so we're going to set up a net torque equation. So it has to be equal to I, alpha, and then we'll say, okay, so the elephant has a, remember the convention is that counterclockwise is positive, so in this case, this direction is positive, this direction is negative, so the elephant is trying to make it rotate this way, so that'd be a positive torque. So the elephant has a mass of 4,600, so we'll say his weight would be the force mg, so 4,600 times g times the distance he is away, which is 10 meters, and then in the negative direction we have the mouse's torque, so we're going to say minus the mass of the mouse, 0.025 kilograms, times g times x for the distance the mouse is away. Now to solve this we could do moment of inertia, so mr squared for each of them, but because we want it to be in equilibrium, that means we don't want any angular acceleration, so we'll say this is equal to 0. So 0 is equal to 4,600 times g times 10 minus 0.025 times g times x, which we want to solve for. We can actually divide g out, okay, and so we'll go ahead and solve this real quick and get that x is equal to, to solve this we get that the mouse would have to be 1,840,000 meters away, which would be the same thing as like 1,840 kilometers away, okay. This is something like 1,100 miles. So basically, if you had an elephant on this platform standing 10 meters away, for this mouse to balance him out, it would have to be standing 1,100 miles away, which is crazy. So clearly this could not be possible, because then we'd have to be thinking about the curvature of the Earth, and really if we're looking at a mouse we couldn't ignore the mass of this platform anyway. But it's kind of a fun problem to think of anyway. So there you go. So that was our first net torque problem. I'll show you one more to wrap up this video. Okay, so in this case we have a cylinder that's getting pulled on by two forces. Okay, one's pulling like this, one's pulling this way. Okay, remember that this direction is positive. Okay, and so the question is, what is the rotational acceleration of this disk? Okay, if this force has a strength of 120 newtons, and this force here has a strength of 60 newtons. So to figure this out, we have to use net torque again. So we're going to say that I times alpha, the net torque, would be equal to the sum of the torques. So we have the torque from F1s, which we'll call torque 1. It's trying to make it rotate this way. So it's pulling this way, which would cause this kind of rotation, which is positive. And then we have from F2, so we'll call that torque 2. And this one is negative because you can see it's trying to pull it back this way. Okay? So we have a couple of steps we have to complete here. First, we have to figure out what I is, in which case I for this is going to be 1/2 mr squared because it's a cylinder. Okay, and then we have to figure out what T1 and T2 are. So this would be F1 times R1, the 12 centimeters. So this would be F1 is 120 newtons. So 120 newtons times 0.12 meters minus, for T2, 60 newtons times 0.08 meters. We have alpha right here. And then 1/2 mr squared will be 1/2 times our m of 90 kilograms times our r of the whole radius would be 12 centimeters or 0.12 meters squared. Okay, so I found the moment of inertia to be 0.648 kilogram meters squared. And so we can simplify this. 14.4 minus the 4.8 is going to give us 9.6 newtons times meters, and we'll divide by the 0.648. Okay, and we'll get an angular acceleration of 14.8 radians per second squared. So what that means is if we have this disk and this one's pulling, it's got a force on the outside 120 like that, force on the inside a little bit of 60 newtons like that, we're going to have a positive angular acceleration. So that means that the disk is going to increase its speed because of these forces. And we could even find out if there's a particle on the outside what linear acceleration it's experiencing. If we wanted to multiply that by the radius, we would get an acceleration of about 1.78 meters per second squared. Okay, so please let me know if you have any questions. So this is basically net force equations as they apply to rotation.